Hello and welcome. Today, we're going to dive deep into one of the fundamental forces of the entire universe, electromagnetism. We're going to build our understanding from the ground up, starting with something you see in everyday life and ending with one of the most powerful equations in all of physics.
So it all kicks off with a really simple question. You've probably done this yourself, right? Why does a balloon stick to a wall after you've rubbed it on your hair? Well, the answer lies in an invisible force, a property of matter that has fascinated people for centuries, starting all the way back with the ancient Greeks. So here's our game plan. We'll start with that ancient mystery, then we'll uncover the basic properties of what we call electric charge, learn how we can move it around, and then finally, we'll put some real numbers to it with the incredible Coulomb's law. Let's jump in.
Our story really begins way back, around 600 BC. The ancient Greeks noticed something odd. When they rubbed amber with fur, the amber would suddenly gain this strange new ability. It could attract little lightweight things, like bits of straw. This was the very first recorded observation of what we now call static electricity, the first tiny clue that electric charge even existed.
So what is this mysterious property? For centuries, it was really just a curiosity. But through simple, repeatable experiments, like rubbing glass rods with silk or plastic rods with fur, we started to figure out the fundamental rules of this thing we now call charge. And through all these experiments, four main ideas emerged. First, there aren't a dozen different kinds of this effect. There are only two. By convention, we just call them positive and negative. Second, things with the same kind of charge push each other away. They repel. Third, opposites attract. And fourth, and this is a big one, charge isn't created when you rub a balloon on your hair, it's just moved around. The total amount of charge in a closed system is always conserved.
Now, here's maybe one of the most mind-blowing discoveries about charge. It's quantized. What that means is it doesn't come in just any random amount. It only exists in these discrete little packets, these integer multiples of a fundamental unit. You can think of it like money, right? You can have 1 cent, 2 cents, or 100 cents, but you can't have half a cent. Charge works the exact same way.
And this right here is that fundamental penny of charge. We call it the elementary charge, E, and it is incredibly tiny, 1.6 times 10 to the minus 19 coulombs. The Coulomb, by the way, that's our standard unit for charge. A single proton has a charge of exactly plus E, and an electron has a charge of minus E. So literally, every charged object in the universe has a total charge that is some whole number times this tiny value. Okay, so we've got a handle on what charge is, but how does it actually behave in the real world? How can we move it around and get it where we want it to go? Well, that depends completely on the kind of material we're dealing with. Materials basically fall into two big categories. You've got insulators, like glass or the rubber of a balloon. In these, charges are bound really tightly to their atoms. If you stick extra electrons on one spot, they pretty much stay put. But then you have conductors, like metals. In a conductor, some electrons form this kind of sea and are free to roam anywhere in the material. So if you add extra charge to a conductor, these mobile charges will spread out super fast, getting as far away from each other as possible until they're all settled on the surface. And this brings us to a really handy idea, grounding. Our planet is just a giant conductor, so we can think of it as a practically infinite reservoir for charge. You can dump charge into it, you can pull charge out of it, and because the Earth is so massive, its own electrical state doesn't really change. It's the ultimate charge sink or source. Okay, using these ideas, we can actually charge a conductor without ever touching it. This process is called induction. Let's walk through it. First, we bring a negatively charged rod near a neutral metal sphere. The sphere's free electrons are repelled by the rod, and they scurry to the far side. This creates a charge separation. We call it polarization. Now, while the rod is there, we ground the sphere. This gives those repelled electrons an escape route, and they flow right off into the Earth. Step 3, we snip the ground connection, trapping the net positive charge that was left behind on the sphere. And finally, when we take the rod away, that trapped positive charge spreads out evenly over the whole sphere. And just like that, we've charged an object by induction. Of course, there are simpler ways too. Charging by friction, that's exactly what's happening with the balloon in your hair. Electrons are literally scraped from one surface onto the other. And then there's charging by contact, which is the most obvious. Just touch a charged conductor to a neutral one, and some of that excess charge will just flow right over. So now we've got a really good qualitative feel for charge. We know its properties, we know how to move it. But, physics is a quantitative science. We need to know
how much force we're talking about. And this is where the French physicist Charles Coulomb comes into the story. Back in the 1780s, Coulomb built this incredibly sensitive device. It was called a torsion balance. Basically, it worked by measuring how much an electric force between two little charged spheres could twist a very thin fiber. By measuring that twist angle very carefully, he could figure out the exact strength of the force. It was just a brilliant piece of experimental work. So what did he find? Well, his experiments revealed three simple, beautiful rules. First, the force is directly proportional to the product of the two charges. Double one charge, you double the force. Second, the force follows an inverse square law. It's inversely proportional to the square of the distance. So if you double the distance between them, the force drops to 1/4 of what it was. And third, the force always acts along the straight line connecting the two charges. All of those findings get wrapped up perfectly in this one equation, Coulomb's law. That F with the arrow over it is our force vector. It's equal to the product of the charges, Q and Q prime, divided by the square of the distance between them, and all of that is multiplied by a constant, K. Now, force is a vector, right? It has direction. That's what the little U or U hat is for. It's a unit vector, which is just a fancy way of saying it's a pointer. It has a length of 1, and it just points along the line from the source charge to the target charge, making sure our force vector points in the right direction. Now that constant, K, is known as Coulomb's constant, and it is a huge number, about 9 × 10⁹. This tells us that the electric force is, fundamentally, a very, very strong force. And this constant isn't just some random number. It's actually connected to an even deeper property of the universe itself, called the permittivity of free space, which we write as epsilon naught. And what's really cool is that, just like gravity, the electric force perfectly obeys Newton's third law. The force that charge 1 exerts on charge 2 is exactly equal in magnitude and precisely opposite in direction to the force that charge 2 exerts on charge 1. It's a perfect action-reaction pair. Okay, Coulomb's law is perfect for two charges. But what happens in the real world, where we have billions upon billions of charges all interacting at the same time? Does the math just become impossible?
Well, thankfully, nature turns out to be remarkably kind to us. The electric force obeys what we call the principle of superposition. This is a super powerful idea, and it basically says that the total force on any one charge is simply the vector sum of all the individual forces acting on it from all the other charges. The force between any two charges is completely unaffected by the presence of a third or a fourth or a billionth charge. This lets us break down a really complex problem into a bunch of simple two-body calculations.
So for a bunch of separate point charges, this principle looks like a big vector sum. The total force on our target charge is the sum, that's the sigma symbol, of all the individual force vectors coming from every other charge in the system. You just calculate each one and add them up, remembering they're vectors.
But what if the charge isn't in neat little points? What if it's smeared out continuously over a volume? We can't just do a simple sum anymore. Instead, we have to pull out the main tool of calculus for summing up continuous things, the integral. We imagine chopping up the volume into an infinite number of teeny tiny charge bits, dq. We define a volume charge density, rho, figure out the tiny force from each dq, and then we integrate, we sum, over the entire volume to get the total force. And this same exact logic works for any shape. If the charge is spread out over a surface, we use a surface charge density, sigma, and we integrate over the area. If it's stretched out along a line, we use a linear charge density, lambda, and integrate along its length. The core idea is always the same. Break the big thing into tiny pieces, use Coulomb's law on each piece, and then use calculus to add it all back up.
And that brings us to a final thought to leave you with. We've seen just how incredibly strong the electrostatic force is. A tiny, tiny imbalance of charge can create forces that we can see and feel every day. So now think about the nucleus of an atom. It's packed to the brim with positive protons, all repelling each other with tremendous force, according to Coulomb's law. So the question is, what in the world could possibly be strong enough to hold that nucleus together against all that repulsion? Well, that's a question for another day. Thanks for watching.